Where did all this come from? In all directions, we find stars, galaxies, clouds of gas and dust, faint plasmas and radiations that span the entire range of wavelengths, from infrared to visible light and gamma rays. The universe is always and everywhere full of matter and energy, no matter where we look or how we experience it. However, it is natural to think that everything comes from somewhere. If you want to know the answer to the most important question of all, the question about our cosmic origins, you must ask the universe itself and listen to what it tells you. Welcome to Real Space. Today we embark on an extraordinary journey, a journey to the beginning of time. How was our universe created? How did it become the seemingly infinite space we know today? What will happen when our universe comes to an end? Scientists have been puzzled by these questions since the beginning of time, and their answers have given rise to some very interesting theories. Since the Big Bang, which marked neither the beginning nor the end of the universe, we continue working to understand it completely. The subject of the origin of the universe and how our world came about has been raised by many civilizations. The insatiable curiosity about its origins remains as strong as it was thousands of years ago. Many civilizations, such as the Mayans, the Chinese, the Arabs, the Greeks, and the Egyptians, believed that a higher power was its creator. Their theories and points of view on how the world was formed differed. They believed that heaven, hell, and earth were in the center. Then the geocentric model emerged. The Greeks theorized that the earth was slightly spherical instead of flat, that there were stars in the sky, and that various celestial bodies orbited the planet. Subsequently, the heliocentric model emerged, which explained that the earth revolves around the sun, which is in the center, according to the notion that the stars are fixed at a distance. Many years later, around the year 2000, Copernicus established his heliocentric theory, which was approved after his death. The universe is composed of everything that can be imagined: nature, the oceans, the world, and even our solar system, according to a study of the evolution of the universe. The Big Bang Theory is the most accepted. Nothing arises from nothing. For something to exist, there must be matter or a component available. What happened in the initial instant to create the materials that caused the Big Bang? And where did that material come from? It is still unknown how our universe arose, or if something existed before, but physicists continue to work to find the answer. To give a meaningful answer to the question of how something can exist from nothing, we need to explain the initial quantum state of the entire universe. Any attempt to achieve this remains highly speculative. Some resort to supernatural forces, such as a designer. However, there are still plausible alternative answers that fall within the scope of physics. These include the multiverse, which is made up of an infinite number of parallel universes, and cyclic models, which experience repeated births. Roger Penrose, physicist and winner of the 2020 Nobel Prize, proposed a tempting but controversial concept of conformal cyclic cosmology. Penrose was inspired by an interesting mathematical connection between a very hot, dense, and small state of the universe, as it was in the Big Bang, and an extremely cold, empty, and expanded state of the universe in the distant future. His radical theory to explain this correspondence is that those states become mathematically identical when taken to their limit. Incredibly, all the matter in our universe could have originated from a total absence of matter. From this perspective, the Big Bang comes from almost nothing. However, the universe did begin 138 billion years ago, and this video is about what happened after it. Music, despite what its name may suggest, the Big Bang was not an explosion in space, but the appearance of space everywhere. Everything existed in a flat dimension 8 billion years, and this video is about what happened after the Big Bang. Music, the Planck era, despite what its name may suggest, the Big Bang was not an explosion in space, but the appearance of space throughout the universe. Everything in the universe was compressed into an incredibly small singularity, a point of infinite heat and density, about 138 billion years ago. That speck was the origin of everything that exists today, the origin of all protons, atoms, and other matter. This was the first known epoch of the universe, also known as the Planck era, a moment so early in the history of the universe that it defies our best understanding of physics. Only 1/10 millionth of a trillionth of a second after the Big Bang, this era took place, and at that moment, quantum fluctuations began to affect space and time. Physicists generally treat general relativity, which operates on enormous cosmic scales, and quantum mechanics, which governs the microworld of particles, independently. But to truly understand the Planck era, we need a complete theory of quantum gravity that merges both. Although there have been attempts, such as loop quantum gravity and string theory, we still do not have a perfect theory of quantum gravity. In these attempts, ordinary space and time are considered emergent, like waves in the ocean, because we are beings rooted in the macroscopic universe. Space and time seem meaningless, but what we experience as space and time is the result of quantum processes that work at a deeper level. We can no longer rely on our ordinary understanding of cause and effect, since in the Planck era, our standard concept of space and time collapses. Despite this, all candidate theories of quantum gravity describe something physical that was happening in the Planck era, some quantum precursor of ordinary space and time. But where did it come from? The physicist Max Planck created a system of units in the late 1890s to simplify the expression of the rules of physics. We could calculate these Planck units using only 5 natural constants, such as the gravitational constant and the speed of light. We could even calculate them using aliens from Alpha Centauri. The Planck units include length, mass, temperature, charge, and time. For a moment, let's consider the Planck length unit. The proton is approximately 100 million trillion times larger than the Planck length. To put this into perspective, if we scale the proton to the size of the observable universe, the Planck length would think about the Planck length unit. The proton is approximately 100 million trillion times larger than the Planck length. To put this into perspective, if we expanded the proton to the size of the observable universe, the Planck length would be a simple trip from Tokyo to Chicago. The 14-hour flight may seem long to you, but it would go completely unnoticed by the universe. It was surprising to discover that the limits of the Planck scale, initially developed as a system of universal units, also turn out to be the limits in which the currently accepted laws of physics operate. During the Planck era, the universe was so small that our laws of physics break down. To delve further into time, we need a new scientific language. Although we cannot observe what actually happens on the Planck scale, scientists speculate that, at this energy, the 4 fundamental forces, gravity, electromagnetism, the weak force, and the strong force, finally combine to form a superforce. Superstrings and quantum gravity are some of the possible phenomena that could dominate at the Planck energy scale. We need a new, unbreakable physics to understand anything beyond the Planck scale. The period of time immediately after the Big Bang, known as the Planck era, began at time 0. The Big Bang ended between 10 and 43 seconds later, equivalent to 1 Planck second. We cannot use current technology to measure the duration of this moment, as it is too brief. These figures exceed our ability to comprehend. The original matter did not exist, since the universe was created in extremely hot conditions. Everything was pure energy. The universe had a temperature of about 100 million trillion degrees Kelvin and was approximately 100 million trillion times smaller than a proton at the beginning of the Planck period. So you get an idea. This is the size of an atom. The typical radius of an atom is around 0.1 nanometers. 1 nanometer is 1/1000th of a meter. Atoms are extremely light and small and are made up of subatomic particles, protons, neutrons, and electrons, which are even smaller and lighter than atoms. The Big Bang created the universe, which has expanded ever since. However, time and space do not exist in the universe until it reaches the Planck scale. Space compacts, but time remains undefined. According to string theory, there were 10 dimensions in the universe during the Planck era, but those dimensions were reduced to 4. One way to visualize the 6 additional dimensions would be as extremely small hyperspheres between the spaces between the basic particles, 4 huge dimensions and 6 microscopic ones. The best way to describe the universe during the Planck era is as a 10-dimensional quantum foam containing Planck-sized black holes that are continuously formed and destroyed without apparent cause or effect. However, the vast unpredictability of the Planck period ends after only 100 million trillion seconds, when the universe cools and gradually grows, which signals the beginning of a new era. Its enormous unpredictability ends after only 100 million trillion seconds, when the universe cools and gradually grows, which marks the beginning of a new era. For a while, the universe does not seem or act as it does now, but in the future our current theories at least have the possibility of explaining what is happening. Gravity, the weak force, electromagnetism, and a strong force are the four fundamental forces that affect everything we do daily, from playing basketball to sending a rocket into space or simply putting a magnet on the fridge. Everything that happens in the cosmos is controlled by these forces. All known interactions in science, from the minuscule to the enormous, as well as those we encounter daily, are caused by these forces. These forces explain how galaxies move, how chemicals react in our laboratories, how atomic nuclei are structured, and why radioactive decay occurs. They explain the real meaning of everyday concepts such as friction and normal force. You surely know gravity, since it has undoubtedly helped you not fall. Gravity is the attraction between two objects that have mass or energy, whether dropping a stone from a bridge, orbiting a planet around a star, or causing the tides. Of the four fundamental forces, gravity is possibly the most recognizable and intuitive, but is also proven to be one of the most difficult to explain. The concept of gravity was first raised by Isaac Newton, who claimed to have been inspired by an apple falling from a tree. It defines the result of the curvature of space-time. Objects deform in the same way that a huge ball deforms a sheet of material in the center, causing smaller objects to fall towards the center. This is similar to how a large object behaves in space-time. Although gravity holds together planets, stars, solar systems, and even galaxies, it turns out to be the weakest of the fundamental forces, especially on a molecular and atomic scale. Think about how difficult it is to lift a ball off the ground, lift your foot, or take a jump. All those actions counteract the gravity of the entire Earth. In addition, gravity has very little effect in comparison to the other fundamental forces at the molecular and atomic level. While the other forces hold things together, the weak force plays a more important role in the disintegration or decomposition of things, although it is only effective at extremely short distances. The weak force, also known as weak interaction, is stronger than gravity. It is an essential subatomic particle for the creation of elements and the energy source of stars. A great part of the natural radiation in the universe is also caused by it. Although its name implies that it is a weak force, it is approximately 10-25 times stronger than the gravitational force within the limit of the nucleus. Due to its relative weakness in comparison with the strong force or the strong nuclear force, it is known as weak force. The weak force plays an important role within the nucleus and is responsible for the beta- disintegration within the nucleus. The nuclear fusion reactions that feed the sun and provide the energy necessary for most forms of life on Earth depend on the weak force. Also, for that reason, archaeologists can use carbon-14 to date ancient bones, wood, and other artifacts that were previously alive. Nitrogen-14, which contains 7 protons and 7 neutrons, is created when one of the 8 neutrons of carbon-14 disintegrates into a proton. Due to the predictable rate of decay, scientists can determine the age of these artifacts. The electromagnetic force between charged particles, like negatively charged electrons and positively charged protons, is also known as the Lorentz force. Like charges repel each other, but opposite charges attract. The force increases with the magnitude of the charge, and like gravity, this force can be felt from an infinite distance, although the force would be very, very small at that distance. The electromagnetic force, as its name suggests, has 2 parts: magnetic and electric forces. Scientists initially distinguished between these 2 forces, but eventually discovered that they are actually parts of the same force. When charged particles are fixed or in movement, the electric component act between them to create a field that allows the charges to interact. However, as soon as those charged particles are set in motion, the magnetic force, the second component, comes into play. As the particles move, they create a magnetic field around them. So when electrons pass through a cable at great speed to charge your computer, telephone, or turn a television, for example, the cable becomes magnetic through the exchange of massless bosons that transport the force, known as photons. In addition, the particles that make up light, the electromagnetic forces, are transferred between charged particles, but there is another type of photons that transport the force and changes between charged particles, although technically they're the same particles as the real and detectable ones. They're virtual and undetectable. Some of the most frequent phenomena, such as elasticity, friction, normal force, and the force that unites objects to each other in a specific form, are caused by the electromagnetic force. It also produces the resistance felt by airplanes, birds, and even Superman when flying. These actions can occur due to interaction between charged or neutral particles. For example, the normal force that keeps a book on a table, instead of gravity pulling the book toward the ground, is a consequence of the electrons of the atoms of the table repelling the electrons of the atoms of the book. The strong nuclear force is one of the four fundamental forces of nature. The strongest is the strong nuclear force, commonly known as the strong interaction. It has a force 6,000 trillion times stronger than gravity. It is 39 after 6, and the reason is that it creates links between the building blocks of matter to create larger particles. Protons and neutrons are formed by quarks, and part of the strong force holds the protons and neutrons together in an atom's nucleus. The strong force only acts when subatomic particles are incredibly close to each other. Just like the weak force, they must be approximately within the diameter of a proton. Once within range, massless charged bosons called gluons transmit the strong force between the quarks and keep them together. A small fraction of a strong force, called the residual strong force, acts between protons and neutrons. Because the protons in the nucleus have similar charges, they repel each other. However, the residual strong force overcomes this repulsion and keeps the particles together within the atom's nucleus. The theory of the Great Unification is a theory that physicists have successfully created to combine the electromagnetic, weak, and strong forces. The strong force separated from the others at the time of the Great Unification, which began approximately between 10 and 38 seconds after the Big Bang. This separation released an enormous amount of energy believed to have caused the rapid expansion of the universe. The universe expanded by a factor of 10 to the 35 and 10 to the 32 seconds during the brief period of time known as musica inflation, going from being incredibly small, smaller than a subatomic particle, to being approximately the size of grapefruit in the blink of an eye. It must be taken into account that inflationary theory refers only to the observable universe. It says nothing about the universe in its totality. Postulating this explosion of exponential growth helps to eliminate two important problems of cosmology: the problem of the horizon and the problem of the flatness of the universe. What we see is basically the same, regardless of the direction we look. With a high degree of precision, the temperatures of the cosmic background radiation are almost identical in all directions of the universe. If we think about it carefully, this really should not be the case. You're looking back in time if you simply look in one direction in space. Since light moves at the speed of light, the light reaching your eye or telescope was emitted years ago. This indicates that there is a limit extending in all directions to about 14,000 million light years. The limit is actually further away because space itself is expanding, but you can ignore that for this example. There is no possibility that anything further away could have come into contact with us. So when you look with your powerful telescope, you can see the cosmic microwave background radiation 14,000 million light years away. Let's call this point. If you look in the opposite direction, 14 billion light years away, let's call this point B. You observe exactly the same type of cosmic microwave background radiation. Normally, This would suggest that all the cosmic microwave background radiation in the universe has somehow spread throughout the cosmos, similarly to heating an oven. Somehow, thermal information is communicated between points A and B. However, given that points A and B are separated by 28,000 million light years, and that no signal can travel faster than the speed of light, there is no possibility that they have communicated in all the age of the universe if there is no way for heat to be transferred between them. How did they reach the same temperature? This is the horizon problem, also called the homogeneity problem. The geometry of the universe, which appears to be flat, especially in light of the new data from the WA map, is the subject of the flatness problem. Even 14,000 million years after the formation of the universe, when the small variations should have grown drastically, the density of the matter and the rate of expansion of the cosmos seem to be almost perfectly balanced. Physicists need an explanation of why the small deviations have not drastically increased, since this has not happened. Did the variations not exist at all? Did they not grow into large-scale variations? Or did something smooth them out? The flatness problem aims to explain why the geometry of the universe seems to be so perfectly flat. These three types of universes are simplified representations of the way in which space naturally curves in the universe. The first is the closed universe, where the universe contains enough matter for gravity to overcome the expansion of space. This type of universe has a positive curvature as geometry, which fits the original model of Einstein, which did not include a cosmological constant. The second is the open universe, where the cosmos will always expand at the same rate, since there is not enough matter to stop it. This spacetime has a saddle shape with negative curvature. The third is the flat universe, in which the expansion of the universe slows down over time, but never stops completely because the density of the matter and the expansion of the universe are exactly balanced between each other. This space has no global curvature at all. In 1980, the astrophysicist Alan Guth proposed the theory of inflation to solve the problems of the horizon and the flatness. In this model, the initial expansion of the universe accelerated at a much higher speed than we see now. According to inflation theory, any detectable large-scale curvature of the cosmos would have been eliminated by the ultra-fast inflation. It could be compared to the growth of a small balloon to Earth size. The local section that you would see would seem very flat, but the balloon is still curved. The visible part of the cosmos seems almost flat due to the enormous inflation of the small universe, which solves the flatness problem. The reason the horizon problem is solved is that, during inflation, space expanded so rapidly, with these nearby regions extending to cover the entire visible universe. However, these nearby regions were scattered throughout the visible universe. The inflation of balloons can be used as a basic model to explain how the universe expands. Each point of the balloon moves away from the center, so a person at any point could feel that he is in the center of the expansion. The spaces between the objects on the surface of the balloon increase as it expands. The universe expanded by a factor of around 10 to the 78 during inflation. This number consists of 26z after the 1, goes beyond the normal political and economic debate about inflation. Let's assume for a moment that someone wrote a message so small that it is unreadable on the surface of the balloon before inflation. The message could be read after inflating the balloon. This implies that the writing on the original balloon is enlarged with inflation, so it works like a microscope. We can also see the quantum fluctuations that were generated at inflation's beginning. In this way, a massive microscope is created that amplifies the quantum fluctuations, which correspond to a size of less than 10 to the 28 centimeters to cosmological distances, by the expansion of the universe during the inflationary era. This leaves traces in the distribution of galaxies and in the hottest and coldest parts of the cosmic background radiation. Now that inflation is firmly established in our understanding of the early stages of the universe, cosmologists have spent the 40 years since Alan Guth's revelation, trying to discover the mechanism by which a universe can explode so suddenly and drastically. The dramatic phases coincide with the cooling and the decrease in energy that mark the end of the great unification of the fundamental forces and the emergence of the strong nuclear force. Some scientists theorize that the disintegration of the X-boson messenger particles, which transported the electrodynamic force, created a strong inflation field transported by a new messenger called inflaton. This new and overwhelming inflationary energy drove the exponential expansion of the universe, which caused the quantum scale irregularities to instantly expand to large-scale structures. The transient quantum fluctuations became enormous regions of overdensity and energy that, over time, would give rise to the clusters and superclusters of galaxies of the current cosmos. The cosmos cooled and emptied as a result of all this expansion, which caused the average energy levels to be reduced 100,000 times. The exact reason why inflation stopped remains unknown to scientists, but when it happened, the inflation field and the disintegration of the particles released radiation and elementary particles to the universe, returning a large part of that energy to the universe during a process known as reheating, similar to water vapor in the atmosphere that condenses into drops of water, forming a cloud. The formation of photons, gluons, and quarks, the fundamental particles, occurred during reheating, but in a state of dense plasma. The quarks and antiquarks began to destroy each other. However, the mutual destruction of quarks and antiquarks gave rise to an excess of quarks for some reasons that are still unknown. This difference or excess of quark matter is why all the galaxies, stars, planets, and people are here today. In addition, the theory of the Great Unification affirms that during this period the three additional fundamental forces were formed: the electromagnetic force, the strong nuclear force, and the weak nuclear force, which then separated the universe as we know it today. The four forces of nature and the rules of physics came into play. Even though the fundamental particles have mass, the universe is still too hot for the quarks to join and create protons and neutrons. The reheating ended approximately at 10 to the 10th part of a second. Because of this, matter can be created completely and in a more expansive universe. The laws of nature are getting closer to being something that we can really understand and music model. We are now entering the universe's third era. The duration of the Elro era was from 10 to 36 to 10 to 12 seconds. Now, as we move through the eras, it begins to make sense how a small singularity was able to expand so rapidly to become the current universe. The electrodynamic week marks the beginning of the modern universe as we know it, due to the fact that the four fundamental forces will be distinct from each other at the end of it. In addition, we will see the creation of the first particles that, over time, would give rise to matter. Most of us are familiar with the electron, the proton, and the neutron when we think of particles. But did you know that there are many other particles and combinations of particles? What exactly are these particles? Let's delve a little deeper. Everyone drives a car, uses a laptop, and has a phone. But have you ever wondered what the history of these materials is? Matter exists around us in four different phases: solid, liquid, gaseous, and plasmatic. The second form of matter is the field, where four different forms of fields are observed. The electromagnetic field and the gravitational field are well known due to the events that take place in our environment. The other two, nuclear fields, occur in the world of atoms. There are two types of nuclear fields, weak and strong, with different intensities. The corpuscular form of matter is composed of two fundamental particle groups. The fundamental particles, also called elementary particles, are the smallest building blocks of the universe. The key characteristic of fundamental particles is that they have no internal structure, which means that researchers think of them as zero-dimension points that do not occupy space. There are millions of different complex molecules inside a single cell. When we zoom in on one of these molecules, we can see individual atoms. Simply put, there are about 40 trillion cells in the human body, and each contains about 100 trillion atoms. However, atoms are not the end of the story. If we could zoom in further, we would see clouds of electrons around the atoms. And if we zoomed in once more, we would find empty spaces. But let's not stop here. If we continue to zoom in, the nucleus would be visible in the center of the atom. However, the story does not end with the nucleus. Further magnification of the nucleus would reveal protons and neutrons attached to one another. These are subatomic particles. Now let's zoom in once more on one of the protons, and we will detect small particles dancing inside. They're the quarks. We call these small particles fundamental or elementary. In the standard model of particle physics, there are 4 force carriers and 12 matter particles, in addition to quarks, which are elementary. So, what classifies something as an elementary particle? If we look at the proton, we see that it is made up of 3 quarks. So, protons are subatomic rather than elementary particles. Elementary particles cannot be divided because they lack substructures. This implies that they are not composed of anything. They are the ultimate and smallest building blocks of our universe. All matter is composed of particles called fermions and force-carrying bosons. Leptons and quarks are the 2 types of fermions. Since leptons do not form groups and function alone, they are classified as solitary particles and are also fermions. They lack internal structure, like all fundamental particles. There are 6 different types of leptons: the electron, the electronic neutrino, the muon, the muonic neutrino, the tau, and the tau-neutrino. When the 6 are ordered according to their mass, the tau and the neutrino TAA are the heaviest in the group, while the electron and the electronic neutrino have the lowest mass. Leptons have an integer charge, which is negative or neutral. Its charge is an integer or a natural number. The charges of the muon and the electron are all negative, -1. In addition, neutrinos have no charge, so as not to be outdone by the leptons' quarks, which are the other type of particles that are grouped and also come in 6 different varieties with some of the most extravagant names found in particle physics. The 6 types of quarks are up, down, charm, strange, top, and bottom. In addition, quarks are also ordered from lightest to heaviest in terms of mass within the group. The bottom quark is the heaviest, while the up quark is the smallest in mass. Antiparticles are particles with opposite charge found in all quarks and leptons. Leptons are solitary particles, as we have already seen. They like to be alone. On the other hand, quarks only exist in groups and are very sociable, so they combine to form composite particles. Composite particles are not considered fundamental, since they are a combination of other particles. Composite particles are particles formed by more than one quark and, like other particles in physics, have a name. They are called hadrons and are divided into 2 different classes: baryons, which are hadrons formed by 3 quarks, and mesons, which are hadrons composed of 2 quarks, 1 quark, and 1 antiquark. Bosons are the fundamental particles that carry force, as we have seen. In the case of fermions, they act as glue. Bosons are also divided into 4 main varieties: the graviton, governed by gravity; the photon, governed by the electromagnetic force; the gluon, governed by the strong nuclear force; and the W+, the W, and the Z, governed by the weak nuclear force. Light particles, or photons, have no mass, so they can travel through the vacuum at the speed of light, 3 million kilometers per second. However, if all elementary particles lacked mass, our universe would be very different. A proton could not trap a massless electron to create a hydrogen atom. In addition, the absence of hydrogen atoms would mean the absence of stars, galaxies, and life as we know it. All elementary particles lacked mass in the first trillionth of a second, but something happened quickly after the era of great unification that allowed some particles to gain mass. But how did these particles acquire mass? To clarify this, several physicists proposed a theory in the 1960s. They suggested that, shortly after the Big Bang, a force field was created and that, when particles interact with this field, they gain mass. Today, we call this field the Higgs field. The universe is full of this field, and, through contact with it, particles such as the W and Z bosons gain mass. The stronger the interaction, the heavier the particle. The difference between the massless photon and the massive W and Z bosons observed in nature today can be explained by the existence of the Higgs field. Other force-carrying particles, such as photons and gluons, remain massless because they do not interact with the Higgs field. There are two ways to identify a field. The electromagnetic field can be detected by observing the particles that interact with it. Another option is to create the photon, a quantum particle connected to a magnetic field, but you cannot manipulate the omnipresent Higgs field. To see it, we must create the Higgs boson, a quantum particle that would be present in the Standard Model along with the other 16 particles, and that would be crucial to explaining the interactions and behavior of matter throughout the universe. By creating the Higgs boson through high-energy particle collisions using accelerators such as the enormous Large Hadron Collider, the Higgs boson decays instantaneously and is incredibly unstable, so it is not easy to detect or observe, since it transforms instantaneously into lighter particles. For example, it could transform into a pair of photons or 4 electrons. Scientists look for the particles left by the Higgs boson by observing the remains of the collision. To better understand this idea, we can use the analogy of water and swimmers. The water, in our example, represents the Higgs field. A fish, being extremely hydrodynamic, interacts only slightly with the field and can move through it very easily. In that case, the fish would resemble a low-mass particle. On the other hand, a man weighing 80 kilograms could move very slowly through the water. That man in our example is a huge particle that becomes massive through extensive interactions with water. The electron is the lightest subatomic particle known, and the top quark is the king of mass in the subatomic world. It weighs almost 350,000 times more than an electron, or the equivalent of an entire gold atom. It is important to note that we do not believe that the larger size of the top quark makes it heavier. No, not really. Scientists believe that the electron and the top quark are exactly the same size. Yes, they both have exactly the same size. The top quark is more massive than electrons simply because it interacts more with the Higgs field. The truth is that none of these particles would have any mass if the Higgs field did not currently exist. The Higgs boson is mentioned more often in the press than the Higgs field. How are these two elements related? The smallest component of the Higgs field is the Higgs boson. We must return to water once more to understand how it works. Everyone knows what water is. As you can see, there is water around you. If you submerge yourself in it, there are no gaps. It is also known that molecules, in particular H2O, make up water. Now you can begin to understand the Higgs boson if you combine these two concepts with the knowledge that water is composed of many separate molecules. The particles in subatomic particles are made up of an infinite number of distinct Higgs fields. Higgs bosons are composed of individual molecules, just like water. Peter Higgs and François Onlet won the Nobel Prize in Physics in 2013 for their theoretical discovery of the mechanism associated with the Higgs field, the theoretical framework that explains how particles get their mass. The particle has earned its place in the Standard Model, and the field its role in the evolution of the early universe. Remember that bosons are not physical elementary particles, but force carriers. This is a huge step towards the presence of physical matter in the universe, since the Higgs field can slow down other particles and impart mass to others, a very strange concept to understand. This field is what allows our universe to support mass. Towards the end of this era, the weak nuclear force and the electromagnetic force finally separate at around 10 to the minus 12 seconds. Now that the universe has cooled enough to allow the four forces to act independently, the laws of nature that we explain in classical physics begin to take shape. Now that the universe has cooled to about 10 quadrillion degrees and the four fundamental forces are separated, the universe had a greater degree of stability. We see the birth of a new era, the era of quarks, defined for the first time by the interactions of matter. It is here that we begin to see the rapid formation of quarks and antiquarks. These particles collide and annihilate each other upon impact. Apart from a normal matter that makes up you and me, there is another type of matter known as antimatter. This type of matter is unique because, when it interacts with normal matter, it can destroy it with an immense explosion of energy. In fact, a single gram of antimatter, upon contact with a gram of matter, would release approximately the same amount of energy as the 1945 atomic bomb that devastated Hiroshima. While the combination of matter and antimatter can create energy, the opposite is also true. Energy can create matter and antimatter in equal quantities. Since the discovery of antimatter in 1931, the evidence has become increasingly solid, and its existence is widely accepted by physicists. One of the strangest twists of nature occurred when an excess of quarks began to accumulate as a result of a process called biogenesis. According to biogenesis theory, the quark was not destroyed in approximately 1 in every billion collisions between quarks and antiquarks. The existence of mass today is due to an asymmetry between quarks and antiquarks. Without it, the particles could have simply collided and destroyed each other indefinitely. However, how is it possible that matter and antimatter in the early universe had such a small imbalance? Although scientists have some theories, we are not certain. For example, in the 1960s, scientists discovered that the universe slightly favors certain subatomic matter particles over their antimatter equivalents. We refer to these particles as quarks, but scientists have another theory, since the difference between quarks and antimatter is insufficient to explain the universe. Neutrinos are very low-mass particles that occur in some forms of radioactive decay, and the largest nearby producer of neutrinos is our own Sun. To determine if the behavior of neutrinos and antimatter neutrinos differs, researchers are building particle accelerators and detectors. If neutrinos and antimatter neutrinos act differently, it could be the answer to the mystery, which would mean that our universe was formed by leptogenesis, that is, by creation from low-mass particles, the accumulation of quarks, and the presence of gluons, a bosonic force-carrying particle, which caused the consistency of the universe to be a densely populated soup of quarks and gluons. It is called that because the observation of particle collisions, music, finally, the era of quarks comes to an end, and a new era begins, the Epoch of Hadrons, which lasted from 10 to 6 seconds to 1 second. At this point, the temperature of the universe reached approximately 1 trillion degrees, which allowed the quarks to combine to form hadrons. As we have already discussed, there are two classes of hadrons, baryons and mesons. A slight asymmetry between matter and antimatter in the previous phase, also known as baryon asymmetry, gives rise to the elimination of antibaryons near the end of this era. Only light and stable baryons, protons and neutrons, remain due to the sufficiently high density of leptons. Protons and neutrons rapidly change between each other under the action of the weak force. However, the universe cooled enough for neutron to proton conversions to slow drastically. From then on, there were approximately 7 protons for each neutron, since helium needs 2 protons and 2 neutrons to form a nucleus, while hydrogen needs only 1 proton. A ratio of 7 to 1 of protons to neutrons would result in an equivalent excess of hydrogen over helium, which is what we observe today. To explain the apparent overabundance of helium in the universe, George Gamow proposed that most of the helium in the current cosmos was created in the first moments of the Big Bang, in less time than it takes to cook a chicken. Gamow developed the theory that the cosmos was formed from a hot soup of particles after the Big Bang. He called this substance elim, which in Greek means shapeless substance from which the elements were formed. He commissioned Ralph Alpher, a doctoral candidate, to find out the processes that led to the production of heavier components from the elim. Gamow and Alpher developed their ideas in an article entitled The Origin of the Chemical Elements. The article Alpha, Beta, Gamma was established as the standard for prestellar fusion and continues to be the basis of our understanding of how high temperatures at the beginning of the universe were able to convert hydrogen into helium through deuterium intermediates. Protium, composed of a single proton, is the lightest form of hydrogen, so these hydrogen nuclei existed as soon as the quarks joined into protons. It is fundamental to remember that neutral hydrogen atoms, which have protons and electrons, are not formed until some time later. The sphere of space that will become the observable universe has a radius of approximately 10 light-years. Now, about 10 seconds after the Big Bang, the temperature was low enough for some deuterium nuclei to form with a proton and a neutron. Unfortunately, the deuterium nuclei were still unstable in this hot cosmic soup due to the high temperature and energy of the particles. If they were hit by a photon, as was inevitable in such densities, these first composite nuclei would have broken apart again. Physicists refer to this as the deuterium bottleneck, and, until it was overcome, nucleosynthesis simply did not progress beyond the fusion of a proton and neutron. It takes about 300 more seconds for temperatures to drop to the point where deuterium becomes more stable and other elements begin to develop. The first deuterium, with its proton and its neutron, is able to fuse with individual protons under the intense compressive force of the entire universe. The result is helium-3, a completely new and stable element. After this, the most common variety of helium appears, known as helium-4, composed of 2 protons and 2 neutrons, is the next creation of the cosmos. The most difficult element to break down is helium-4, whose nuclei are the most stable atomic nuclei known. This, along with the circumstances that existed in those first hundreds of seconds, caused most of the free protons in the early cosmos to be absorbed by helium and not decay. Not even 13,800 million years after this intense burst of helium formation and the birth and death of countless stars, the universe still contains about 23% helium. This simple observation provides solid proof in favor of Alpha's theory. 8,000 million years after this intense burst of helium formation and the birth and death of countless stars, the universe still contains about 23% helium. This simple observation provides strong evidence in favor of Alpha's theory, and this is where we see another example of how the initial conditions of the universe were randomly adjusted. We already know that if the ratio of protons and neutrons had been different, much of the ordinary matter in the universe would have decayed into uncharged and unreactive neutrons and helium. But similarly, even with the ratio of protons and neutrons that we were given, if the matter of the cosmos had been more compact at the time of the Big Bang, it would have decayed into uncharged and unreactive neutrons and helium. But similarly, even with the ratio of protons and neutrons with which we count, if the matter of the cosmos had been more compact at the time of Big Bang nucleosynthesis, even more helium would have formed. The lack of reactivity of a universe composed predominantly of helium would have meant that chemistry would have been impossible from that moment on, which would have led us back to the gloomy prospect of a universe without galaxies, without stars, and without us. Fortunately, this was not the case, since even when so many hydrinos settle into their stable helium nuclei, the universe is still full of latent energy that could be used for further fusion. Now, the race is on to generate as many new elements as possible before the ambient energy of the universe drops too much after 20 minutes of universal existence, or about 1,200 seconds of intense cosmic nucleosynthesis. The nuclear furnace finally slows down and dies, as it is too cold for more nuclei to form. Even if it is too cold for more nuclei to form, even if it is still burning by human standards. Currently, there are only 4 elements in the universe: hydrogen, helium, lithium, and beryllium, and only the first 3 will survive long enough to witness the first stars and serve as the main fuel for the creation of the other 98 elements that occur naturally in the current universe. Due to the ephemeral stability of those beryllium nuclei, for now, there are a billion photons for every particle of composite matter and 12 hydrogen nuclei for every helium nucleus. But with these basic ingredients, the stage is really set for the formation of everything else, even the deuterium and tritium that scientists fused in California in 2012, which was first formed in the heat of a newborn universe 13,800 million years ago, after the particles merged and separated to form nuclei 8,000 million years ago. After the particles merged and separated to form nuclei, the primordial mixture of hydrogen, helium, and traces of lithium and deuterium nuclei marked the end of the nucleosynthesis era and gave rise to the formation of the first stars. These were the first nuclei of the universe, which went from being slightly larger than a grapefruit during the era of great unification to having a radius of about 300 light-years today. The universe has grown in size due to its continuous expansion. There is a big difference. The universe cools as its expansion continues and temperature decreases. During this period, the universe's temperature ranged between 10 and 3000 Kelvin. The fusion stopped when the universe cooled to some point. We see how the nuclei join other particles later to form atoms and then galaxies and stars. After the era of nucleosynthesis, we now enter the era of nuclei. The only thing that changes is that this era marks nuclear fusion's end. The universe is getting bigger because it is expanding, though more slowly than the previous era. The size of the universe has increased by a factor of 1,000. Our universe is now a huge space full of ionized particles. You can see that the universe ages as it expands. The universe's pressure decreases continuously as the universe expands. Volume and pressure have an inverse relationship. So, as the volume of the universe increases, its pressure decreases. The nuclei no longer fuse together. The universe is still just a ball of hot plasma containing charged particles. Throughout this period, nuclear fusion could not continue because the temperature was too low. However, the temperature remained high enough to keep all the atoms ionized and prevent electrons joining nuclei. Until about 500,000 years ago, the photon particles that produce light were also scattered throughout the universe along with the electrons, but they could not react because they were trapped in an equilibrium in which the photons could not escape. The era of nuclei created a lot of light, but it could not be seen anywhere due to the extreme density of the universe. The photons always collided with an electron or a nucleus before continuing their trajectory, which prevented the universe from having light. The universe became opaque to light. The duration of the era of nuclei ranges from 3 minutes to 500,000 years. After 500,000 years, the cosmos finally cooled to 3000 Kelvin, at which point the hydrogen and helium nuclei began to absorb free electrons. Since photons could no longer interact with electrons outside of very small energy ranges, most of the gas became transparent, allowing photons to finally escape the plasma and pass through the universe. These photons are what we now experience as the cosmic microwave background. When we look at the universe, we can never see back in time. Beyond 500,000 years, which is the time of the last scattering of photons, before this, the hot surface of the universe was all we could see. Now we will see what happens to atomic nuclei, electrons, and photons as we move into the next era. Now we will enter the era of atoms, which began when the photons separated from the hot surface of the universe was all we could see. Now we will see what happens to atomic nuclei, electrons, and photons as we move toward the next era. Now we will enter the era of atoms, which began when the photons separated from matter and the nuclei began to fuse with electrons. After the atoms were formed, matter no longer had any effect on photons or light particles, so the photons that currently form light in neutral atoms make up the universe. Space was literally made possible by the formation of atoms. The temperature of the universe throughout this era ranged between 300 and 60 Kelvin. The universe became transparent as a result of matter and photons decoupling due to the decrease in temperature. That means that when these neutral atoms were formed, electromagnetic radiation, including light, could travel through space much more freely than before, making the universe basically transparent to light. We can think of this process as the following example. Imagine a parking lot full of cars. Our nuclei are the vehicles, and there are many people or free electrons between cars. If you try to make your way through such a dense mass of cars and people, you would most likely be pushed or deflected in all directions. However, if humans got inside the cars, that is, if electrons joined the nuclei to form atoms, there would be enough free space to pass between them without being deflected. The era of recombination is the name given to this phase of the universe's evolution, since it saw the combination of nuclei and electrons to create stable atoms. The era of decoupling owes its name to the fact that, during this period, light was finally able to separate from matter. The reason we see the CMB in low-energy light is solely because the expansion of the cosmos has caused the photon's energy to shift to the red or relocate to the red end of the light spectrum. The actual energy of these photons was in the ultraviolet, a shorter band. Since then, the Explorer satellite has measured this background radiation and found that it fits perfectly into the spectrum of a black body at a temperature of 273 Kelvin. This perfect black body radiation that comes from everywhere is solid proof that we understand the universe at least up to 500,000 years before the Big Bang. However, the cosmic microwave background shows us that the structure and temperature of the universe were almost constant, with fluctuations of only a few degrees compared to now. It was a very different environment. There are no galaxies, there are no stars. We only see this extraordinarily uniform temperature. Astronomers aptly call this era the structure and temperature were almost constant, with fluctuations of only a few degrees compared to today. It was a very different environment. There were no galaxies, there are no stars. We only see this extraordinarily uniform temperature. Astronomers aptly call this era the Dark Age. The universe continued to expand and cool after recombination, the beginning of during which the glow of the Big Bang shifted to infrared wavelengths. This dark age of the universe, which lasted hundreds of millions of years and began around 400,000 years after the Big Bang, was the last period in which the universe was truly empty. No planets, no suns, no galaxies, no life, and no other celestial bodies, leaving only a fog of hydrogen atoms created during the Big Bang and left to their fate in the dark. Today, telescopes around the world are trying to capture a glimpse of that primordial hydrogen, known as neutral hydrogen, in order to determine when the Dark Age finally ended and the first galaxies were formed. Music. In past times, we have witnessed the emergence of the universe from a small singularity to a massive universe full of atoms. Let's investigate the age of galaxies to learn how the universe reached its current state. Our universe continues its evolution within this timeline. The force of gravity caused matter to clump together, forming galaxies. The formation of the first galaxies marks a key transition in the evolution of the universe's structure. These galaxies changed the intergalactic medium from neutral to ionized thanks to their second-generation population. 2 stars, 0 metallicity population. The 3 stars and sources driven by black holes, such as mini-quasars, X-ray binaries, etc. This process is known as the era of reionization. The formation of stars and quasars occurs during reionization. They begin to release powerful radiation that causes the neutral hydrogen atom to break down into protons and free electrons. Reionization eventually ends, and hydrogen atoms are formed again. It is believed that the energy of these first stars, the first galaxies, and the incredibly bright quasars with black holes in the center helped reionize the hydrogen gas. In this case, ionization is the process by which the energy of the star extracts electrons from the atoms of surrounding gas, causing them to shine. Since this is the second time the gas has been energized since the Big Bang, this era is known as reionization. As a result of the combined energy of these early stars and galaxies, light was able to travel further into space than it had previously. Probably, the most pressing question in astrophysics is discovering more about the early formation of stars, which will help us understand how the first galaxies or groups of stars formed. The recently launched James Webb Space Telescope was created largely to answer this question, as its infrared capabilities allow it to see objects with a large redshift, such as these early galaxies. Afterwards, the galaxies gradually approach each other due to gravity, forming clusters and superclusters. The density difference in the cosmic microwave background created a way for stars to develop and ignite. These stars eventually came together, forming galaxies. The universe is expanding with a diameter of 93 billion light-years at this time. The temperature of the universe is between 60 and 273 Kelvin during this era, which spans 1 billion years from the Big Bang to the present. As new galaxies form, the universe continues to evolve. In fact, we're living in the age of galaxies right now. Dark matter appears to be widely distributed around the visible stars within galaxies. Galaxies collide with each other because the halos of dark matter make them appear larger than they really are. The collision of small galaxies leads to the fusion and formation of giant galaxies. The two basic components of the entire universe are matter and energy. Most of the matter in the universe is invisible, and most of the energy is unknown, which poses a major challenge for scientists. If much of the universe is invisible to us, how can we study it? Scientists will remain at the forefront of the search for dark energy and dark matter as our observation techniques become more sophisticated. The distribution of dark matter in merging galaxy clusters, such as the Bullet Cluster, is mapped with the help of NASA's Chandra X-ray Observatory and optical telescopes. X-ray observations reveal a heated shock front where the gas from the clusters collided and slowed, but gravitational lensing measurements reveal that dark matter remains separate from normal matter and is not affected by the collision. One theory suggests that some dark matter particles annihilate in an explosion of intense radiation, causing them to disappear. Signs of dark matter annihilation have been identified using the Arizona High-Energy Radiation Imaging Telescope System, which is equipped with gamma-ray detection capabilities. Researchers are examining how dark energy and gravity have collided throughout the history of the universe by comparing observations of galaxy clusters with experimental models. Thanks to modern methods, we can calculate the amount of dark matter present in a galaxy by measuring the curvature of light from background sources. We can estimate the galaxy's mass by measuring the degree of that curvature using this gravitational lens technique. When the mass we calculate from the curvature and the mass we can directly observe do not match, we know that dark matter must be present. Music of the universe we know that dark matter exists, even if we cannot see it. Approximately 45% of the visible matter coincide. We know that there must be dark matter. Music of the universe. We know that dark matter exists, even if we cannot see it. About 5 billion years ago, our solar system formed from a dense cloud of interstellar gas and dust. The cloud collapsed, possibly due to 5 billion years ago. Our solar system formed from a dense cloud of interstellar gas and dust. The cloud collapsed, possibly due to the shock wave from a nearby exploding star called a supernova. When this dust cloud collapsed, it formed a solar nebula, a rotating, swirling disk of material. The planets formed in a thin disk that rotated around the sun, which formed in its center. The moons evolved around the giant gas planets, similarly to all the other planets in our solar system. They originated from a disk of gas and dust that rotated around the young sun. Drag forces joined the dust particles to form clumps of rock that eventually evolved into what scientists call planetesimals, which reach hundreds of kilometers in diameter. After these protoplanets collided, Earth, our home planet, was created. Music in the current universe, matter dominates radiation. The protons, neutrons, and electrons, the known components of the atoms, as well as the mysterious dark matter, constitute the greater part of the matter. The greater part of the radiation of the universe is found in the form of cosmic background of microwaves. Surprisingly, in spite of its extreme weakness, the radiation of the cosmic background of microwaves continues having more energy than all the stars and known galaxies. Music together. This is because, although they are emitters of extremely potent radiation, the stars and the galaxies only constitute a very small part of the space. From a physical point of view, our universe seems incredibly perfect. If it was different, the life as we know it, the planets, the atoms, and everything else would not exist. Would exist. Our universe, in all its greatness, is a perfectly tuned symphony of physical laws, fundamental constants, and cosmic forces. Our universe is not just a random collection of matter and energy. It is a masterpiece of precision. As we continue exploring the cosmos, we marvel at its elegance and wonder if the delicate balance that sustains our existence hides secrets still to be revealed, a cosmic ode that waits for us to decipher its notes. That is why I want to tell all those that are watching this video that they can have anything that they want. They only have to ask it to the universe. All they have to do is let go and feel good, and the universe will surprise them with beautiful miracles. So let us look upward, embrace the mystery, and enjoy the inspiring perfection of our universe.